Hi everyone, this is the third video for complex numbers, and in this video we're going to look at Moivres' theorem. Now so far in this topic we've learnt about complex numbers and what they are, and operations with complex numbers. We've looked at the complex number plane and vector representation, and then we looked at mod-arg form or polar form and exponential form. In this lesson, just one thing, Moivres' theorem. So let's begin. If z is equal to r cis theta, then z squared is equal to r cis theta multiplied by r cis theta. We just learnt about multiplying complex numbers that are written in mod-arg form. We multiply the moduli, we add the arguments. We're going to get r squared cis 2 theta. Okay? Similarly, or likewise, z cubed is equal to z squared times z, which is r squared cis 2 theta multiplied by r cis theta. Okay, same method, r squared times r is r cubed, cis 2 theta plus theta is 3 theta. Okay, so it leads me to a pattern. Z to the power of 4 would be r to the power of 4 cis 4 theta. So here's my conjecture, that z to the power of n is equal to r to the power of n cis n theta, and that's actually de Moivre's theorem. It's no point just having a conjecture though. What we've got to do is prove it. And we're going to use mathematical induction to prove de Moivre's theorem. So step 1, we're going to show it's true for n equals 1. We just need to substitute 1 for n. Now we started with this statement that z was equal to r cis theta, so it is true. It's true for n equals 1. And step 2 is to assume true for n equals k. So substituting k in here, we get z to the k is equal to r to the k cis k theta. Step 3, prove true for n equals k plus 1. Now I always like to start with a required to prove statement with my mathematical induction, so that's what this stands for, required to prove. We want to show that z to the k plus 1 is equal to r to the k plus 1 cis k plus 1 in brackets times theta. Alright, so let's start with the left hand side. Z to the k plus 1 is equal to z to the k times z. We already know what z to the k is, that's our assumption. So let's substitute that in, and z is r cis theta. Alright, the same method we just used. R to the k times r is r to the k plus 1. Cis, add the arguments k theta plus theta. Probably the easiest of mathematical inductions you'll ever do. All I have to do now is factorize this, and I actually have the answer. See? So, it is true for n equals k plus 1, therefore by the principle of mathematical induction it is true for all n. Here's an example. If z is equal to 1 plus root 3i, find z to the power of 5. Now we could expand 1 plus root 3i to the power of 5, but that would be really tiresome and maybe prone to error. Instead, it's much simpler if we put it into mod-arg form or polar form and use de Moivre's theorem. So let's do that. R is equal to the square root of 1 plus root 3 all squared, which is the square root of 4, which is 2. And theta is equal to inverse tan of root 3 over 1, which is pi on 3. And so z is equal to 2 cis pi on 3, and z to the power of 5 is equal to 2 cis pi on 3 to the power of 5, which is to the power of 5 cis 5 pi on 3. And depending on the question, we could leave it in polar form. So we could just write it as 32 cis. Oh, but hang on a minute. This is outside the bounds of our principal argument. This is greater than pi. Do you remember how to get it back in there? We're just going to subtract 2 pi from it. So that's going to give us negative pi on 3. So we could leave it as 32 cis negative pi on 3. But let's turn it to Cartesian form. So expand it out. Cos of negative pi on 3 plus I sine of negative pi on 3. All right, first thing we want to do, which quadrant is it in? It's down here. So cos is positive, sine is negative. And they're both going to be equivalent in value to cos pi on 3 or sine pi on 3. All right, let's work this out. So cos of negative pi on 3 is the same as cos of pi on 3, which is a half. Sine of negative pi on 3 is the same as negative sine of pi on 3, which is negative root 3 on 2. Substituting that in, and then tidying it up, I get 16 outside of 1 minus root 3i. Now, de Moivre's theorem works with exponential form as well, but it's a little bit more intuitive. If z is equal to re to the I theta, then z to the n is equal to r to the n e to the I n theta. Now think about it. What we're doing is raising this to the power of n. So that's going to be r to the n. And then when I raise a power to a power, I multiply the indices. So e to the ni theta, or however you want to write it. Here's an example. If z is equal to root 2 e to the negative 3 pi and 4i, find z squared and z to the negative 1 in Cartesian form. All right, pretty easy. We're just going to square our complex number. Root 2 squared is 2. E to the negative 3 pi on 4i times 2 is negative 3 pi on 2i. Now, because we want it in Cartesian form, we need to expand this like this. Now, I notice straight away that this is outside of our domain, isn't it? It's less than negative pi. But it's a boundary value. This is negative 270. So I actually know this. So I don't need to adjust it. Cos of negative 270 is 0. And sine of negative 270 is 1. And you can just work that out on your calculator. So our answer here is 2i. All right, now let's do this one. Z to the negative 1, I'm taking my complex number and raising it to the power of negative 1. Same thing. Root 2 to the power of negative 1 is 1 on root 2. And then e to the negative 3 pi on 4i multiplied by negative 1, which of course is positive 3 pi on 4i. Okay, we need to expand this out. So I'm going to get 1 on root 2 and cos of 3 pi on 4 plus I sine of 3 pi on 4. All right, we're going to need to work this out. Which quadrant is this in? Let's draw up a quick diagram. And we've got all stations to central. 3 pi on 4 is up here. So sine is going to be positive, cos is going to be negative, and they're going to be equivalent to cos or sine of pi on 4, because I'm just doing pi take away 3 pi on 4. So cos of pi on 4 is root 2 on 2, and it's going to be negative. Sine of pi on 4 is root 2 on 2, and it's going to be positive. There it is. And tidying it up, I end up with negative 1/2 plus 1/2 I. Now, not surprisingly, de Moivre's theorem can also be used for the conjugate of z. In other words, z conjugate to the power of n is equal to r cos theta minus I sine theta in brackets to the power of n, which is r to the n cos n theta minus I sine n theta in brackets. If you wanted to prove that, you would prove it by mathematical induction. All right, I'm going to do something sneaky. Have a look at this line. Instead of n theta, I've got negative n theta. Instead of n theta here, I've got negative n theta, but I've adjusted this sign. How can I do that? Let's think about it. Cos is an even function. So that means if I take the negative angles here, so this part of the graph, and I flip it over here, it's going to exactly match the graph for the positive angles. Okay, so that means that cos n theta is equal to cos negative n theta. It's not the case with sine though. Sine is an odd function. So if I pick up my graph here for the negative values, flip it over, it's almost the same, but it's going to appear down here. It's going to be the opposite sign. So instead of having n theta, if I put negative n theta, I can have a negative out the front. And that's going to put it into cis form for me. And so it's equal to r to the n cis of negative n theta. Okay, we're going to move on to the harder applications of de Moivre's theorem. Expand cos theta plus I sine theta all cubed to show that cos 3 theta is equal to 4 cos cubed theta minus 3 cos theta. This is a really typical question that they like to ask. What we're going to do is expand it in two ways, using the binomial theorem and then using de Moivre's theorem. Let's start with the binomial theorem. So we've got cos theta plus I sine theta all cubed. That gives us cos cubed theta plus 3 times cos squared theta times I sine theta plus 3 times cos theta times I squared sine squared theta plus I cubed sine cubed theta. Okay, now if you don't remember how to do that, you need to go and practice. So remember these coefficients 1, 3, 3, 1 come from Pascal's triangle. They are 3c0, 3c1, 3c2 and 3c3. All right, let's tidy that up and we get cos cubed theta plus 3i cos squared theta sine theta minus 3 cos theta sine squared theta minus I sine cubed theta. All right, now using de Moivre's theorem, much easier, we get cos 3 theta plus I sine 3 theta. Now, we want to show this. So I can see this cos 3 theta here, and I can see bits of it sitting in here. What is missing from this is the sines and also the i's. So what we're going to do here is equate the real terms. So cos 3 theta is going to equal cos cubed theta minus 3 cos theta sine squared theta. And there it is. It's slightly different, isn't it? We don't want this sine squared theta. But I happen to know that sine squared theta is equal to 1 minus cos squared theta. So let's substitute that instead. And expanding these brackets, I get cos cubed theta minus 3 cos theta plus 3 cos cubed theta, which is 4 cos cubed theta minus 3 cos theta. Hence, show that cos cubed of 13 pi on 12 is equal to negative 5 root 2 minus 3 root 6 all over 16. And we're going to use the fact that 3 pi on 4 plus pi on 3 is equal to 13 pi on 12. All right, because it says hence, I'm going to use the thing that we just proved, which was cos 3 theta is equal to 4 cos cubed theta minus 3 cos theta. All right, we're wanting to show that cos cubed something is equal to this. So this is going to be key. So even if I don't know exactly what to do in this situation, I'm going to start by making this the subject of this equation. In other words, 4 cos cubed theta is equal to cos 3 theta plus 3 cos theta. Divide by 4, and we've got that. All right, the next step, instead of theta, I'm going to put 13 pi on 12. I'm going to put it in there, and in there, and in there. It's going to be a bit messy. Okay, 3 multiplied by this is going to cancel into that 12 and leave me with 4. So I've got cos 13 pi on 4 plus 3 cos 13 pi on 12 all over 4. So hopefully you're with me so far. Now, cos of 13 pi on 4, I know. It's an exact value. I mean, it's way outside the domain, but because it's got a denominator of 4, it's going to be related to pi on 4 somehow or other. So I'm always looking for denominators of 6, 3, and 4. Oh, and 2, because 2 will give me boundary values. So those I know the exact values of. This one here, I've got no idea. We'll leave it for a bit. So I'm going to take this and I'm going to subtract 2 pi and subtract 2 pi. Actually, on the calculator, I'm going to go 13 on 4, take 2, take 2. It's going to give me negative 3 pi on 4. Okay, we're back in our domain. And I've left that alone. All right, what is this equal to? Cos of this. Which quadrant is it in? Let's think about that for a second. It's down in here. And in that quadrant there, cos is negative. So it's going to be equal to negative cos of pi on 4, which is negative root 2 on 2. All right. So let's make that substitution. See that there? Now, instead of the 13 pi on 12, because I don't know what that is as an exact value, I'm going to use this hint they've given me. 13 pi on 12 is 3 pi on 4 plus pi on 3, and that's going in here. Okay? Now, hopefully you remember what the expansion of this is. It is in your formula sheet. So this is cos of x plus y, or whatever you want to call it. So it's cos of 3 pi on 4, cos of pi on 3. Take away sine of 3 pi on 4, sine of pi on 3. Okay, so there's the expansion there. Okay, so now we need to work out all of these. So we've got cos 3 pi on 4, cos pi on 3, sine 3 pi on 4, sine pi on 3. All right, we sort of worked this one out before, but we worked out cos of negative 3 pi on 4. It's actually going to be the same. This is in the second quadrant. It's negative root 2 on 2. Cos pi on 3 is cos 60, that's a half. Sine 3 pi on 4, that's in the second quadrant, it's positive. So it's positive root 2 on 2. And sine pi on 3 is root 3 on 2. So putting that all in, now what we need to do is expand through this bracket here. We get quarter outside of negative root 2 on 2, take 3 root 2 on 4, take 3 root 6 on 4, which gives us negative root 2. I'm just expanding now. On 8, take away 3 root 2 on 16, take 3 root 6 on 16. This is what we want. Are we there? Nearly. I just need to double top and bottom here, and we will end up with negative 5 root 2, take away 3 root 6 all over 16. So long question. Fairly typical of what they ask though. So let's finish off with a past exam question. Let z equal cos theta plus I sine theta. By considering the real part of z to the power of 4, show that cos 4 theta is equal to cos to the power of 4 theta minus 6 cos squared theta sine squared theta plus sine to the power of 4 theta. So this is another one of those questions where we're going to expand it two ways, binomial theorem and then to Moivres theorem. Okay, so z to the power of 4 is equal to cos theta plus I sine theta to the power of 4. The easiest one is de Moivres theorem, so let's do that first. It's cos 4 theta plus I sine 4 theta. Now let's expand it the other way using binomial theorem. A bit messy, let's have a look at it. I've done it all in one go, so you might need to do it a bit slower. This is cos to the power of 4 theta plus, this is 4c1, cos cubed theta times I sine theta. There it is. And that's going to be plus 4c2 cos squared theta times I squared sine squared theta. So that's why we've got a negative there. Plus 4c3 cos theta times I cubed sine cubed theta. And then finally plus I to the power of 4 sine to the power of 4 theta. All right, hopefully you understood all of that. Now we need to equate the real parts. So we've got cos 4 theta is equal to cos to the power of 4 theta, not this one, minus 6 cos squared sine squared theta, not that one, plus sine to the power of 4 theta. Look what we want, and that's actually it, isn't it? So we're finished. Hence or otherwise find an expression for cos 4 theta involving only powers of cos. All right, so this is what we had, because it says hence. And all we want is powers of cos. We need to get rid of the sine squared theta and the sine to the power of 4 theta. All right, that's 1 minus cos squared theta. And this is sine squared theta all squared. So I can have 1 minus cos squared theta, that's sine squared theta there, all squared. Does that make sense? Expand this out, and tidying it up, we're going to get 8 cos to the power of 4 theta minus 8 cos squared theta plus 1. And that's it. All right, that's the end of this video. We have more to do on de Moivres theorem, but we need to cover polynomials first. So that's going to be the next video.